In this video, we're going to discuss some probability problems that are going to require us to use our counting techniques. So all the definitions we know for different probability situations are the same. So the sample space is still going to be the total number of possible outcomes for our experiment, for the actual action we're taking. The event is going to be the set of outcomes that we're interested in, specific events that we want to focus on, specific possible outcomes. But in this situation, in order to calculate the numerator and the denominator for our probability, we're going to have to use some of these counting techniques we've discussed. So we've talked about the fundamental counting principle. That just says if we want to perform a sequence of operations, we multiply the number of ways we can do each step, and that's going to give us the total number of possibilities. And then we talked about how to calculate a number of permutations. So remember, permutations, we take a group as a whole, pull a subset out, and then we're rearranging the subset in a particular order. So it's the number of ways we can choose a subset and then arrange that subset. When we're talking about a permutation, remember the order we put things in matters. And then also combinations. So a combination is similar to a permutation, but a combination order doesn't matter. So we're just taking the subset. We're not worried about what order we put things in. We're just taking a subset out of the larger group. So sometimes counting with respect to the sample space, with respect to the event in question, is going to require us to use some of these techniques. Okay. So in a situation involving permutations or combinations, the probability of a specific event will have, number one, a numerator containing the number of permutations or combinations in the event, in other words, the specific outcomes that we're interested in, and number two, a denominator containing the total number of possible permutations or combinations, the total number of subsets and arrangements potentially. So we're going to start doing a couple examples where we kind of break it down and look at the numerator and denominator individually. And then we're going to look at more complicated examples where we're going to have to make some of these determinations on our own. When in doubt, always break it down though and think back in terms of what probability means. So we're talking about an experiment. We're performing an action or a sequence of actions. We want to know, number one, how many ways can that action go? How many total outcomes are there? That's always going to be the denominator for our probability. And then number two, how many ways can we get the specific outcome or specific set of outcomes involved in our event? In other words, the ones we actually care about, the ones we're interested in the probability of. That's always going to be the numerator for our probability. So for example, suppose 3 men and 3 women line up at a checkout counter in a store. We want to know what's the probability of specific outcomes. So we're going to break this down. We're going to ask a couple questions, and then the very last question will be the question involving probability. So the first question, in how many ways can these people line up? So we've got 3 men, 3 women. We just want to know in how many different ways can we arrange these people in a line at the checkout counter. So since we're talking about a line at the counter, the order matters. Changing the order changes who goes first, who goes second. So order is implied here, so this means this is going to be a permutation. Now we're arranging all of them. So there's 3 men, 3 women. There's 6 people in total that we're arranging. So we have 6 to arrange. We're taking all 6 and arranging all of them. And again, it's a permutation because we care about the order they end up in. If we rearrange them, it's considered a different possible outcome. So this is going to be 6, permutation 6. So remember, type your N first. So 6. I'm going to go to PRB, and then I'm going to use the option for permutation, which is the first option. So 6 permutation 6, which is going to be 720. So just based on choosing from this group of 6 and arranging all 6, there's going to be 720 ways to line these people up in line. Now we're going to get more specific. In how many ways can they line up if the first person in line is a woman and then the line alternates by gender? So in other words, woman, man, woman, man, woman, man, specifically in that order. So think of this as still involving the same action. The action is we're arranging people in line. There's 720 total ways to do that. Now we're interested in a specific kind of arrangement, so specifically arranging them so that they alternate by gender, and we start with a woman, we end with a man. Automatically, there are going to be fewer ways to do this than there are total ways to arrange people in general, just because we now have stricter requirements in terms of what these orderings can look like. Now we're arranging 6 people. This is a little bit different from just a permutation because now we're looking at going by gender, not just choosing from the 6 in total, but choosing a woman, a man, a woman, a man. In other words, we've got to break it down a little bit more than just looking at the group of 6 in total. So this is a situation where we can use the fundamental counting principle. Think about the steps in the process. Well, the process here is choosing the location for each individual person. So in other words, looking at, say, 6 slots in line and making a choice for each of those 6 slots in line. So think of this as a 6-step process. So spot 1 in line has to be a woman. So we have to ask ourselves, how many ways are there to choose a woman to be the first person in line? Well, we have 3 women to choose from. So for the first spot in line, we have 3 ways to make the choice for that particular spot. So there's going to be 3 ways to choose the first woman in line. And then we're going to multiply by how many ways we can do each subsequent step. So the next step is going to be to choose the man that comes after her. Well, how many ways are there to do that? Well, there's 3 men. So there's going to be 3 ways to choose the man that comes after her in line. Now keep in mind, once we've assigned the first slot and the second slot in line, we've now taken 1 person out of the pool of women. We've taken 1 person out of the pool of men. We now have fewer people to choose from to put in the remaining spots because 1 man and 1 woman have already been put in line. So once we get to the 3rd space in line and we're supposed to put another woman, because again, we alternate by gender, that means we now only have 2 women to choose from. One of them was already put in slot 1. Now there's only 2 more to choose from. So there's 2 ways to assign the 3rd spot in line. Same thing with the 4th spot, which is now the next man. We chose 1 to put in the 2nd spot. Now there's only 2 more to choose from for that particular spot. Now keep in mind, because we started with 3 of each gender, once we've assigned the first 4 places in line, there's only 2 people left to choose from. One's a man, one's a woman. So that means there's only 1 way to choose a person for the last 2 spots in line, because there's only 1 person left of each of those genders. So if we multiply the number of ways to perform each of those steps together, we get a total of 36. So that means there's 36 different ways to create a line that looks like this. So each individual is different. 3 options for women, 3 options for men, and then decreasing options, but again, alternating by gender as we go. So 36 ways to arrange people based on this particular type of arrangement. So now let's put this together. How does this fit into the context of probability? We want to find the probability that the first person in line is a woman, and then the line alternates by gender. In other words, we want to find the probability that if we perform the experiment of taking 3 men and 3 women and arranging them in line, that's the experiment, we want to determine the probability of this particular event as described. We want to determine the probability that the first person in this line is a woman, and then we alternate by gender. In other words, what's the probability that we get an outcome that looks like this? Well, remember, the definition of probability says the denominator is going to be the total number of outcomes for the experiment. Now remember, the experiment is just the action in general. What are we doing in general? Regardless of specific outcomes, what's the physical action that we're taking? Well, the physical action that we're taking is arranging people in line. We're arranging 6 people in line. This is a specific outcome, specific way of arranging people in line, but the actual physical action we're taking is just arranging people in line. Well, we determined if there's 6 people to arrange, then there's 720 ways to arrange these people in line. So the denominator of our probability is going to be 720. Now, the event we're interested in is that the line starts with a woman and then alternates by gender. In other words, what we determined for part B. Well, how many ways are there to create a line that starts with a woman and then it alternates by gender? Well, we determined there's 36 ways to do that. 36 based on the fundamental counting principle, multiplying together how many ways there are to place each person into their particular spot in line. So 36 ways to get this event that we want out of the 720 ways to just line people up in line based on having 6 people to line up. So our probability is going to be 36 out of 720. Now again, depending on how we want to report our answer, maybe we want a reduced fraction, maybe we want a decimal. How do we take care of both of those? Well, take the 36 and divide into 720. So 36 divided by 720. Here's your decimal. Notice we don't even have to round this. This is a terminating decimal. So 0.05 is the decimal form. But what if we just want the reduced fraction? Remember, we can convert that to a fraction. So right over the table button, there's fraction arrow, decimal arrow. In other words, convert back and forth between these two forms. It's green, so it means we have to use this button with the second button already hit. So second and table says take this number we just found and then convert forms. So I do that, and that's going to convert me to 1 over 20. So if you see something like this and you're not sure what to do to reduce it, of course, when in doubt, these are both even, so they could both be reduced by 2. That would at least be a place to start, but you can use the calculator and that'll save you a little bit of time. So the probability that we arrange people such that the line starts with a woman and then alternates by gender is going to be 1 out of 20, or 0.05. In other words, 5% of the time, if we were to randomly arrange these 6 people, this will be the random arrangement we choose, 5% of the time. Okay, let's look at another one. A political discussion group consists of 5 Democrats and 6 Republicans. 4 people from this group are selected to attend a conference. Okay, so let's do the same kind of thing. Let's break this down and then we'll put this in the context of probability. So first question, in how many ways can 4 people be selected from this group of 11? So this tells us in general what the experiment might be if we're looking at probability. We have a group of people, 5 Democrats, 6 Republicans, and we're choosing 4 to attend a conference. So our first question again was, how can we pick the 4 out of the 11? How many different ways are there to do that? Notice there's no restrictions on who we choose or how we choose. We're just choosing 4 out of the 11. Now, because this is take a large group and choose a smaller group from it, this is either going to be a permutation or a combination situation. Now, how do we know which one it is? Remember, permutations involve an ordering and combinations don't. Now here we're just choosing a committee. We're just choosing a group, a collection of people. It doesn't say anything about putting them in order or assigning them hierarchical rows, anything like this. We're just choosing 4 out of the 11. So because there's no order involved in this situation, that means we're looking at a combination. So we're going to have to use the combination formula. So if we're just generally looking at this group of 11 and choosing 4 from that, our N is going to be 11. And then our R is going to be 4. So 11, combination 4. So let's type that in. So 11, probability. We're choosing combination, not permutation. And then we're taking combination with subsets of 4. So there's going to be 330 ways to do that. So based on just choosing a subcommittee from this group, there's 330 ways to choose a group of 4 people out of this group 11. Now again, that's no restrictions involved. That's just choosing randomly 4 people out of the group of 11. Now the next question is, in how many ways can 4 Republicans be selected from the 6 Republicans? So suppose we choose just 4 Republicans from the 6 Republicans. So we've got 6 to choose from, and we're choosing 4. So again, it's a combination. It doesn't say anything about order. It doesn't say we're ranking them or we're assigning them roles. It just says we're picking 4 out of the 6. So it's a combination. So 6 combination 4, which is going to come out to 15. So here's our first probability question. The question is, find the probability that the selected group will consist of all Republicans. In other words, if we're taking this group of people, this group of 11 people, and choosing 4 from the group, what's the probability that we'll choose a group that's all Republicans? In other words, if we just randomly choose, how likely is it that our choice is just going to be a group of all Republicans, just choosing randomly? Well, again, it's going to be the number of ways we get that outcome divided by the total number of ways to get an outcome for the experiment. So the experiment here is choosing 4 people to attend the conference, choosing 4 people out of 11. The event we're interested in is this particular outcome, 4 Republicans only, just Republicans represented in this particular group. Well, there's 330 different total outcomes for choosing the committee of 4. There's 15 ways to specifically choose 4 Republicans. Now, how do we know that the numerator has to be that number 15? If we're considering the situation where we're just choosing Republicans, the only way we could make sure that we just chose Republicans is to only choose from the group of Republicans. If we looked at a larger group that had both Democrats and Republicans, we can't guarantee that any choice is going to be strictly Democrats or strictly Republicans. So if we're talking about a specific outcome based on a specific group, we have to make sure that we're making our choice from that particular group exclusively. So if we want a group that's all Republicans, we have to make sure we're choosing just from the 6 Republicans. Now again, you have to fall back on the experiment. What's the experiment? It's choosing 4 people. So choosing 4 people from the group at large, 330 ways to do that. Choosing 4 people from the group of Republicans, just choosing Republicans, means we're only choosing from 6 out of the 11. So 6, and we're choosing 4. There's going to be 15 ways to do that. So 15 ways to get the outcome we want, divided by 330 ways to perform this experiment and get an outcome. So 15 out of 330 is going to be our probability. So again, we can reduce that. That's going to be 0.05 as a decimal, roughly. And then if we want that as a fraction, the exact fraction is going to be 1 out of 22. Now let's take it up a notch. So another counting question, and then we'll look at the associated probability. In how many ways can 3 Republicans be selected from the 6 and 1 Democrat be selected from the 5? So keep in mind, we're choosing 4, just like we were choosing 4 Republicans here. We're choosing 4 people, but now it's going to be 3 Republicans and 1 Democrat. How many ways can we make these choices? This is going to involve not only a combination, but also the fundamental counting principle. There's 2 steps in this process. Choose your Republicans from the Republicans. Choose your Democrat from the Democrats. Perform that sequence of 2 operations. There's a number of ways to do step 1. There's a number of ways to do step 2. We multiply those numbers together, and that's going to give us the total number of ways to perform the sequence of operations. Now, each of the individual steps involves a combination. We're choosing a subset out of the group involved. We're choosing a subset out of the other group, and those are giving us the individual counts for the individual steps. So for our first step, we're choosing 3 Republicans out of the 6. So 6 to choose from, we're choosing 3. Again, we know it's a combination because there's no ordering involved here. We're just choosing 3 out of the 6. So 6 combination 3 comes out to 20. There's 20 ways to choose 3 out of the 6. Now we also want to choose 1 Democrat out of the 5. So 5 to choose from, and we're choosing 1. 5 ways to do that. So step 1, 20 ways to do that. Step 2, 5 ways to do that. We multiply those results together, and that's going to be 100. So there's 100 ways to make these 2 choices together and then get an outcome making these 2 choices, performing this 2-step process. So let's relate this to the probability. We want to find the probability that the selected group, again, the 4 people we're choosing to go to the conference, Find the probability that the selected group will consist of 3 Republicans and 1 Democrat, this specific combination. Well, again, from the definition of probability, it's how many ways we get this outcome, 3 Republicans and 1 Democrat, divided by the total number of outcomes for the experiment. In other words, choosing the 4 out of the group at large. So 330 ways to choose 4 out of the group at large. And we just determined there's 100 ways to choose 3 Republicans and 1 Democrat. And that's the event we're interested in, 3 Republicans and 1 Democrat. So our probability is going to be the 100 ways we can get the outcome we want, divided by the 330 possibilities in total. So this one's pretty easy to reduce. Notice that common 0 at the end. You can just cancel that out and you get 10 over 33, which does not reduce any further. If you approximate that, it's approximately 0.3. So in other words, about 30% of the time, if you randomly choose a group of 4 out of this group of 11 described, about 30% of the time, you're going to get this particular combination, 3 Republicans and 1 Democrat. Okay, so these kind of problems hold your hand a little bit. It's breaking it down. Notice it gave us the question representative of the total number of possibilities. And then we also got the questions we needed to answer in order to determine the outcomes in a particular event. Normally, you're just going to be asked the probability question, which means you then have to break it down yourself. What's the experiment? Well, how many ways can we get an outcome for the experiment? And how many outcomes are representative of the event that we are interested in, the particular specific combinations that we're interested in. So let's look at a couple examples, breaking it down ourselves. Okay, if you are dealt 3 cards from a well-shuffled deck of 52 cards, you find the probability that all 3 cards are face cards. Okay, start by defining the experiment. What is the actual action, operation, sequence of operations that we're doing? Think about what's physically happening. What's physically happening is that we're dealing 3 cards. So that is the experiment. We're dealing 3 cards. Okay, so that means when we're looking at probability, the number of ways to deal 3 cards out of the deck is going to be the denominator. So how do we choose 3 cards out of the deck? That's going to be the total number of outcomes for this particular experiment. Notice there's no restrictions here. So the denominator, the total number of possibilities, is completely absent of restrictions. We're just dealing 3 cards. We're looking at the number of ways to deal 3 cards out of the deck. So 52 to choose from in total, and we're dealing 3 out of the 52. So we're taking a subset of 3 out of a larger set of 52. So 52 combination 3 comes out to 22,100. So in other words, in terms of 3 card hands from a well-shuffled deck, there's 22,100 different possible hands that you can get that consist of 3 cards. Now, our event that we're interested in is all 3 of the cards we get are face cards. So we want to know, how can we get events that look like this? How many outcomes are there that would be representative of just getting face cards? Well, here's where we have to make a little bit of a leap. How could you make sure that you deal from the deck and only get face cards? The only way you could do this is if you took the deck and you threw away the bunch of the cards. The only way that you could make sure that you're only getting face cards is if you're only dealing from the set of face cards. So in other words, take out all the aces, take out everything from 2 to 10, take out anything that's not a face card, and then just deal 3 cards from that set of face cards. That's the only way you could guarantee that this particular event would take place. So then the question is, if we sort of stack the deck so that it looks like that, how many ways are there, how many different possible outcomes are there that are representative of just getting 3 face cards? Well, if we throw away everything else in the deck, we would still be left with 12 cards. There are 12 face cards. So you have a jack, a king, a queen, a king from the 4 suits. So 4 times 3 is going to be 12 face cards in total. So from that 12, we have to choose 3. So it's a combination, again, because order doesn't matter, but we're choosing 3 out of the 12. So 12 combination 3 comes out to 220. So there's 220 ways to get 3 face cards out of this deck, to get exclusively face cards. So the denominator for our probability is the total number of outcomes. The experiment is dealing 3 cards. Well, there's 22,100 ways to deal 3 cards with no restrictions involved. The event we're looking at is the event where all 3 cards are face cards. Well, if we choose strictly from the 12 face cards, 3 cards, there's 220 ways to get a subset of just face cards. So the numerator for our probability is going to be 220. So 220 divided by 22,100. Okay, so that's going to be our probability. We have to reduce that. So again, you can use your calculator. So type that in as a division, convert that to a decimal, and then use that arrow frac option to take your decimal and convert it back to a fraction. Notice this is a pretty small decimal, so it's approximately 0.01. So what that means is about 1% of the time, if you're just randomly dealing, it's a well-shuffled deck, about 1% of the time you can expect to get a hand of 3 cards that are just face cards. So we could say that this is a pretty unlikely event. It's not all that likely, if things are truly random, that this will be the outcome that we get. Okay, let's look at another situation. Now we're dealing 4 cards. So we went from 3 cards to 4 cards. We're dealing 4 cards from our well-shuffled deck. We want to find the probability of getting exactly, specifically, 2 aces and 2 kings. Okay, so go back to the experiment. The experiment is dealing 4 cards. So the denominator for our probability is going to be the number of total outcomes we get from dealing 4 cards. So in order to choose 4 cards, we have 52 to choose from, and we're choosing 4. It's a combination because, again, order doesn't matter. So 52 combination 4 is 270,725. Notice the difference here. We went from 3 cards to 4 cards, and notice how much the count went up just by adding that additional card in. So adding in just 1 card or just 2 cards drastically increases the number of possibilities you have for your combinations and for your permutations. So this is the number of outcomes we can get from our experiment of dealing 4 cards. So that's going to be our denominator for our probability. Now the event we're interested in is getting specifically 2 aces and 2 kings. So think of this again as 2 steps. We want specific outcomes. We want 2 different specific outcomes. So we have to choose our aces and our kings separately. So kind of like with the face cards, think about the only way you could get just aces or just kings. Well, you'd have to make sure you're dealing just from a stack of aces and from a stack of kings. So think about just making a stack of aces and making a stack of kings, and then dealing 2 out of each of those piles. Think about taking the little piles and then shuffling them and then dealing 2. So to choose 2 aces, we're choosing out of the 4 possible aces that we have in the deck. So 1 for each suit, 4 suits in total, so 4 aces in the deck. So 4, and we're choosing 2. So 4 choosing 2 comes out to 6 in this case. Now we're also choosing 2 kings. So we have to take a pile of kings, just 4 kings, and then deal 2 out of that pile. Throw away the rest of the cards in the deck. Just look at the aces, look at the kings individually. So for our kings, again, 1 per suit, 4 suits, so 4 in the deck in total. And again, we're choosing 2. So notice these 2 counts, these are the same, but we do have to do them separately because each one of these choices is representative of choosing from a different group. So we do have to think of this as 2 steps and 2 separate choices. We can't choose out of a pile of 8. We have to choose out of a pile of 4 for the aces and a pile of 4 for the kings. Each of those counts, again, is going to come out to 6. So 6 times 6, we can call that 6 squared. That's going to be 36 in total. So out of the 270,725 ways to deal 4 cards, 36 outcomes specifically represent dealing 2 aces and 2 kings exactly. So our probability is going to be 36 out of 270,725. If we convert that to a decimal, this is what we get. So if you think about the places, this is the tenths, the hundredths, the thousandths. This is the 10,000ths place. So as a fraction, you can think of that as roughly 1 out of 10,000. In other words, if we're randomly dealing cards from a well-shuffled deck, about every 1 in 10,000 deals, you'll deal a hand that has 2 aces and 2 kings. So extremely rare, very, very rare. Much more rare than dealing all face cards. So all face cards is about 1 out of every 100 deals. This would be about 1 out of every 10,000 deals. So much rarer because notice it's a much more specific outcome. This is just 3 face cards. They can be any face cards we want. These have to be specifically 2 aces and 2 kings. So much stricter requirements, so much less likely to happen. Okay, let's look at another situation. Here's one that's always interesting. If you play the lottery, how smart is it to play the lottery? What are the odds? What's the likelihood of actually winning the lottery? Let's see what that looks like. So we're going to consider a version of Powerball. Okay, so the game is set up so that each player chooses 5 different numbers from 1 to 69. So you have all the numbers from 1 to 69. You choose 5 different numbers from that group. You can't choose the number more than once. Choose 5 different numbers. And you're going to choose 1 Powerball number from 1 to 26. So that's how you fill out your lottery ticket. Choose 5 numbers from 1 to 69, and then choose your Powerball number from 1 to 26. So twice per week, 5 white balls are drawn randomly from a drum containing the 69 white balls. So in other words, those are representative of the first choice you made. And then 1 red Powerball is drawn from a drum containing 26 red balls. So that again is representative of the second choice you had to make on your lottery ticket. So a player wins the jackpot by matching all 5 numbers drawn from the white balls in any order and matching the number on the red Powerball. So in other words, to win the whole thing, you have to match every single number. All 6 numbers have to match. So you chose the 5 different numbers here from 1 to 69, and you chose the 1 number from 1 to 26. All of those numbers have to match what's chosen, which is random. We're assuming the choice is random. They spin the bins, they pull out the balls. The choices there are random. You have to match them all in order to win the jackpot. So our first question is, with a single Powerball ticket, what is the probability of winning the jackpot? How likely is it that you will actually win the jackpot? Okay, so what's the experiment here? What are we actually doing? We're filling out a lottery ticket, okay? Or we can think of matching a lottery ticket to the numbers that were chosen, or matching the numbers that are chosen to a lottery ticket. That's what we're actually doing. So think of it maybe in terms of the balls that are being drawn. How many different ways are there to draw all the balls you need to represent a lottery ticket? So we draw 5 white balls, we draw 1 red ball. So 5 white balls from 1 to 69, and then 1 red ball, 1 to 26. Okay, and that represents the choice each time they actually run the lottery. So think of these as the 2 steps you have to take in order to get all the balls representative of the lottery outcomes. So for drawing the 5 white balls, that's step 1, we have 69 to choose from, so numbered 1 to 69. So we're choosing from 69 of them, we're choosing 5 of them. Now it's a combination because the order doesn't matter. If you match all the numbers on your ticket but they're in the wrong order, it doesn't matter, you still win. So 69, combination 5. So that comes out to 11,238,513. That's the total number of ways that we can draw the 5 white balls out of the bin containing ones numbered from 1 to 69. Okay, so a little bit over 11 million ways to do that. Now we also have to draw a Powerball, but notice this is a second step. It's not going to be one bin containing a bunch of white and red balls. It's going to be a bin with white balls. So we draw from there for step 1. And then it's going to be a bin of red balls. We draw 1 from there for step 2. So for drawing the Powerball, we have 26 to choose from. and we're choosing only one. So there's 26 ways to take 26 and choose only one. So this is step 1 for drawing the balls. This is step 2. To perform both steps at the same time, we multiply the total number of possibilities together for each step, which gives us 292,201,338. So this is the total number of ways they can draw the 6 balls when they're drawing balls for the lottery. So think about the drawing of the balls as being the same thing as picking the numbers for the ticket. You're picking 5 numbers representative of those white balls. You're picking 1 number representative of the red balls. So filling out a ticket and drawing the balls from the bins is actually the same thing in terms of the steps that it looks like and how many ways you can do each of the steps in the process. So this is the number of ways they can spin it and draw this combination of balls. This is also the number of ways you can fill out a lottery ticket by choosing 5 numbers of one type and then 1 number to represent your Powerball number. So this is going to be the denominator for our probability. The question is what is the probability of winning the jackpot? In other words, filling out a ticket such that the balls drawn matches the ticket that you filled out. Well, this is the number of ways to draw balls, number of ways to fill out a ticket. So this is going to be the denominator. It's the total number of possibilities. Well, how many ways can you completely match all the numbers? How many matching ways are there? Well, the only way you can win the jackpot is by matching every single number. Every single one of them has to be the same. There's only one way to do that. There's only one set of correct numbers. Remember, rearranging the numbers doesn't matter. So we're not worried about rearrangement, anything like that. We're just worried about having the correct set of numbers. Well, there's only one correct set of numbers. This is the total number of sets. There's only one set that's actually correct based on what's chosen from the bins when they actually run the lottery. So the numerator for our probability is going to be 1. There's only one outcome that represents you winning the jackpot. There's only one way to win the jackpot out of the 292 million possible ways that you can fill out a ticket and that the numbers can be drawn. So that's going to be our probability. Now I want to show you what this looks like in a calculator. So we have 1 divided by 292,201,338. Particularly when you're typing big numbers like this, double check that you actually typed what you intended to type. It's very easy to mistype a digit. But there we go. Notice how big that is. Count the zeros. So 1, 2, 3, 4, 5, 6, 7, 8 zeros in front of that 3. Now I want to see if we're going to end up with scientific notation. So let me do this on the graphing calculator as well. 1 divided by 292,201,338. There we go. Good. This is what I wanted to see. I want you to look at this particular way of writing this. Notice this is a little bit different than what came up on the scientific calculator. So the scientific calculator gave you a number that had an actual just decimal expansion. It just had zeros, and then it ended at the 3. What does this mean? Because this looks like it isn't the same answer. This E with the -9 means scientific notation. In other words, that's representative of this particular decimal times 10 to the -9 power. What that means from a practical standpoint is that if you take the decimal point and move it 9 places to the left, and then fill in zeros where you didn't have zeros before. How do we know that this is the same as what's on the scientific calculator? Well, picture actually taking those steps. In other words, taking the decimal point, moving it 5 places to the left. If we move it 1 place, okay, then it moves it in front of the 3. We have to move it an additional 8 places and then fill in zeros for every jump that we do. So that would give us a total of 8 zeros and then the decimal point in front of that. We would still have all of the digits after that. They just come after the 3, so they're further down the decimal in line. Well, that's the same thing we have here. It's just this is rounded so that we don't see any of the digits at the end. So remember, there's 8 zeros there, then there's the 3. So again, this is rounded, whereas this particular version is not, and then we have the scientific notation, but these two mean the same thing. So if you have a graphing calculator and you see this notation, this just means, the e to e negative 9 just means take this decimal and move it 9 places to the left and then fill in with zeros. As you can tell, that's a very, very, very small number. This is pretty close to 300 million. So think of it as every 1 out of 300 million tickets is actually going to match. So in other words, if you filled out 300 million tickets, then yes, you'd be guaranteed to match the numbers. But you'd have to fill out 300 million tickets in order to be sure that you've picked a set of correct numbers in order to actually win the jackpot. So suffice it to say, it's extremely, extremely rare to win the jackpot. If it costs, for instance, $2 per lottery ticket, and you have to buy 300 million tickets to guarantee that you win, well, that's $600 million just to play the lottery and guarantee that you win. So clearly, playing the lottery, not super beneficial. The likelihood of you winning, very low. But keep in mind, typically someone wins. At some point, someone's going to win. It's just because so many people play, and eventually, from a probability of standpoint, eventually someone will win. But it's likely per individual that anyone ever wins. Okay, so one outcome is good out of 292 million outcomes in total. Now let's change it around slightly. So hitting the jackpot is not the only way to win a monetary prize. So for example, a minimum award of $50,000 is given to a player who correctly matches 4 of the 5 white balls, in other words, drawn from the 69, and also matches the Powerball. So find the probability of winning this consolation prize. In other words, find the probability of getting a ticket that matches 4 out of the 5 white balls and then matches the Powerball. So we have to think about what that kind of ticket would look like. So imagine the balls have already been drawn. You're picking a ticket to match those balls, but not match it entirely. We're only matching 4 of the white balls, but one of the white numbers we've chosen is actually incorrect. Okay, so we've got to break this down again. Now it's the same experiment. We're still drawing 6 numbers in total, drawing 5 white balls, drawing 1 red ball. The experiment is the same, so the denominator for our probability is the same. We're taking the same sequence of actions, and in total, the number of ways to do that is still the same. So the denominator of the probability does not change. What's going to change is the numerator, because we're interested in a different event. So the first event was winning the jackpot. There's only one way to win the jackpot, so the numerator was 1. Now we're winning a consolation prize by matching 4 out of the 5 white balls and then the 1 Powerball. So it's not entirely obvious that this is the case, but this is actually a 3-step process. Why is it 3 steps? Well, we have to think about what's going on with this ticket. We're matching 4 numbers, so choosing 4 matching numbers is going to be 1 step in the process. We also have to match the Powerball. That's going to be another step in the process. Now those 2 are obvious. We have to choose those. Those are essentially the same as here. What's the final step? Well, we have to think about what a lottery ticket looks like. The lottery ticket requires that we have 6 numbers. 4 of the white numbers matched, and then 1 of them doesn't match. We have to pick 6 numbers in order to fill out the ticket. We pick 4 numbers that are correct, but in order to fill out the ticket, we also have to pull 1 additional number. It just so happens that that 1 additional number we picked was an incorrect number. So there's 3 steps here: matching 4 white numbers that are correct, matching the Powerball so that it's correct, and then also choosing 1 more white number, one that happens to be incorrect, in order to fully fill out the lottery ticket. So let's look at each of these steps. So option 1, or step 1, matching 4 correct balls. Well, think about how many ways there are to match white balls. How many of them are actually correct? Well, every time they draw balls for the lottery, there's going to be 5 white balls drawn. We've matched 4 out of them. So we have 4 correct balls out of the 5 total correct balls that are possible. So out of the 5 that are correct, we're choosing 4 of them. We lucked out and we chose 4 of them. We just didn't get all 5. So we have 5 possible ones and we're choosing 4 options from the 5 possible correct options. So 5 combination 4. As it turns out, there's 5 ways to do that. Okay, now we're choosing the Powerball. There's only one correct Powerball, so there's only one way to choose the Powerball. So there's only one way to match the Powerball. So there's only one way to do step 2. The last step, again, the one that's not really obvious, but we have to then fill out the ticket. We chose 4 correct white numbers. We need an additional white number, but it needs to be a number that's incorrect in order to match this particular event as described. Well, how do we guarantee that we choose an incorrect white number? So again, imagine the balls have already been drawn and we already know what the numbers are. They chose 5 balls. Well, how do we know we have one that's incorrect? We know we have one that's incorrect if it's representative of one of the numbers that's still in the bin. The numbers that are correct have now been drawn out. The numbers that are incorrect are the ones that are still in the bin. It's the white balls that haven't been drawn. So the incorrect numbers are the ones that are still in the bin. How many of those are there? Well, if we've drawn 5 white balls, there's still 64 in the bin. So in terms of choosing one ball that's incorrect, it's incorrect if it was chosen from the 64 that are still in the bin of white balls. So from the 64 that are still in that bin, we're choosing one of them in order to fill out the remaining number in the ticket. So 64 combination 1, there's going to be 64 ways in order to choose an incorrect ball. So we're choosing 4 correct balls, step 1. That's going to be 5 ways to do that. Choosing the Powerball, only one way to match that because there's only one correct Powerball. And then in order to complete the ticket, we're choosing 1 additional white number, but it's chosen from the 64 that turn out to be incorrect. So 64 combination 1 comes out to 64. Because we're performing this sequence of operations, we multiply the number of ways we do each step together. So 5 times 1, technically, times 64. 5 times 64 comes out to 320. We take 320 divided by the total number of ways to draw the balls, the total number of ways to fill out a lottery ticket, which reduces down to 160 over 146,100,669. Now this is still a very small number, but this is actually quite a bit bigger than the number before. Notice we have fewer zeros after the decimal, which means this particular event is substantially more likely than this one. This one has 8 zeros. This one has 1, 2, 3, 4, 5 zeros. Much more likely, but is it still really likely overall? No, of course not. This is still a very unlikely event. This would be the tenths, hundredths, thousandths, 10,000ths. Let's see, count that again. Tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths. So this would be 1 out of a million. So in other words, about every 1 out of a million tickets will be a ticket that fits these qualifications where we match 4 of the correct numbers, match the Powerball, and then just have 1 incorrect number. So suffice it to say, playing the lottery, typically not very beneficial from a probability standpoint. People win every day, which based on these numbers is honestly shocking. Individual to individual, it's very unlikely that any individual single person wins, but yet people win all the time. So just something to keep in mind. So probability can help us determine when these kind of situations make sense, when games of chance make sense to play, and when they don't. Do they favor the player? Do they favor the house?